Hello everyone. Today I'll show the solutions to problems 5 and 6 of round 158 of the Prairie Math League high school round. So, for problem number 5, we have two pieces of string with lengths x and y. Length x and y. The string of length x is spanned into an equilateral triangle here, and the other string is bent into a regular hexagon. Both have equal area, and we wish to find y over x. Now, notice that the side length of the equilateral triangle is x over 3, because it's x but split into 3 parts. And similarly, the hexagon is split into sides of y over 6. Now, to calculate the areas, we simply note the equilateral triangle area formula. Equilateral triangle of side length s has an area equal to s squared square root of 3 over 4. Now, a hexagon is just basically 6 equilateral triangles. So, a hexagon with side length s will have area equals 6 times x squared over square root of 3 divided by 4. Now we can just plug in x over 3 and y over 6 to get this, which we can solve for y over x to be square root of 2 over square root of 3. Now we can try rationalizing the denominator to get square root of 6 over 3. Unfortunately, this is not one of the option choices. So instead, we're going to match them with one of the option choices, we're actually going to try rationalizing the numerator instead. This gets us 2 over square root of 6, which is option choice D. Now for problem 6, this is AMC 12B problem 19 or AMC 10B problem 21 of this year's AMC. Each one of 23 balls is randomly placed into one out of 3 bins. What is closest to the probability that each of the bins will have an odd number of balls? So these are our bins. We can have each bin either has an even or odd number of balls. So there's we can have even, or say for instance 2 balls here, 4 balls here, 8 balls here. If we're just dealing with 14 balls, we can have even, or we could have something like even, odd, even. But for simplicity, we're going to consider all our cases to be kind of unordered. So what I'm trying to say is either there's 3 evens, 1 odd, 2 odds, or all odds out of all the bins. So this basically reduces our entire problem into 4 cases of number of bins. Now we need to find the probability from each. So these are our 4 states, and we need to find the probabilities from each state into each other state. So let's start with even. There's a probability 1 that the next one will have even, odd, because you're putting in a single ball into 3 bins, each of evens. No matter which bin you put into, that bin is going to be odd, and the rest are still going to stay even. So the probability is 1. Now for even, odd, so 2 evens and 1 odd. There's a 1 over 3 probability that you're going to put a ball into the odd bin and back at even. So this is 1 over 3, and 2/3 probability to end up placing a ball into an even bin, getting even, odd. Now the rest of the cases are basically symmetric about this, because we can just replace the odds with evens, and we basically get the same probabilities but reversed. So this will be 2 over 3 and 1 over 3, and this will be 1. Now from here we can make a table starting from the first few ends. So from 0, 1, 2, 3, 4, 5, and hopefully all the way to some sufficiently large number so that we can spot a pattern. Now we start with, at the beginning we have no balls, so they're all empty, and since 0 is even, it means we have 3 evens. Then we just follow the table. Follow this diagram. So after 1 round, we have a 1 chance from going from here to here. From 2, after we have 2 balls, we now use this probability to get 1 over 3 and 2 over 3. Now 3 is where things start to get a bit complicated. There's a 1 chance that this goes here, but there's a 1 over 3 chance that goes to all 3 odds from the 1 even 2 odd state, and a 2 over 3 chance to go to 2 evens 1 odd. And 2 over 3 times 2 over 3 plus 1 over 3 times 1 is 7 over 9, and 1 over 3 times 2 over 3 is 2 over 9. Now we basically follow the same process, keeping consistent with the diagram here, just basically weighing all the probabilities, and we get this, this, etc. And now we can notice a pattern. This thing, the number on the outside, like two evens or three evens or three odds, is always three. Let's say this is x, then this number is always 3 times x, like, or close to 3 times x, because like 3 times this is 60 over 81, which is approximately 61 over 81. Now, and also notice that they alternate because parity arguments, I guess. You can't have after you put in 5 balls, you can't have 3 evens, because otherwise that would mean you have an even number of balls, which is contradiction. So which basically means that this is 0, 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 and it basically forms like a checkerboard pattern as we continue. And we can if we generalize this, we say that for 2k balls, for an even number of balls, the probabilities are approximately like k and 3k, x and 3x for some number x. And for 2k plus 1, or like an odd number of balls, it's approximately 3x and x. So in particular, for 2023 balls, this is an odd number. So the probability of having 2 evens and 1 odd is approximately 3x, and the probability of having 3 odd balls is approximately x. Wait, this is approximately 3x, yeah. Approximately 3x and approximately x. And we can just solve a simple algebraic expression, because these two have to sum to 1, because that's how probability works. And we see that x is 1 over 4. Now, therefore, the probability of having three bins with an odd number of balls after 2023 balls is approximately x, or 1 over 4, which is option choice C, and we're done. Alternatively, we can take a far more rigorous approach to this table. Rather than simply just trying to generalize to this and hoping it works, we can use induction. So if you take a look at these numbers, we can model them to be, for evens, we can model them to be these algebraic expressions, and for odds, these algebraic expressions. To find them, you just notice that first of all, these sum to 1, for instance. I mean, like these sum to 1, and 7 over 27 times 3 is equal to 21 over 27, which is equal to 20 over 27 plus 1. And so from there, it takes a bit of effort, but you can kind of deduce these expressions. And for odd, you get these expressions. This also shows that the desired probability is this for 3 odd case. And this rapidly converges to this, because this term basically cancels out as n grows really large. And again, this is 1 over 4, which is option choice C. The proof for the induction is an exercise. Probably too big to fit in this one small video. But anyways, thanks for watching.